Welcome. Today we're going to be talking about Fermat's theorem, or sometimes called Fermat's little theorem. And I'm going to start by illustrating it with an example. Let's work mod 7. P is 7, 7 is a prime. And 7 minus 1 is 6. And let's do just some computations. 2 to the 6th is 64. And mod 7, that's 63 plus 1, which is 1 mod 7. And let's look at 3 to the 6th. So we're going to take a bunch of numbers to the 6th. 3 to the 6th is 729. And 729 is 728 plus 1, and 728 is divisible by 7. So again, this number is 1 modulo 7. And 4 to the 6th is what? Let's see. 4 to the 6th is 4096. And that's 4095 plus 1. And let's see, 4095 turns out to be 585 times 7. So again, this number is 1 modulo 7. Okay, how about 5 to the 6th? Well, let's see, 5 to the 6th is 15,625. But let's do this a better way. 5 to the 6th mod 7, which is what we're interested in. Well, 5 is the same thing as minus 2. So we can replace it with minus 2 mod 7. And we already know, well, let's see, minus 2 is minus 1 to the 6th, and 2 to the 6th mod 7. And minus 1 to the 6th is just 1. And we already know 2 to the 6th is 1 mod 7. So again, this comes out to be 1 mod 7. All right, let's see, let's do one more. 6 to the 6th mod 7. Well, again, 6 is minus 1. So this is really minus 1 to the 6th, and that's obviously 1 mod 7. So what I just checked is that if you take any number 1, 2, 3, 4, 5, or 6 and raise it to the 6th, you get 1 modulo 7. That is, and now let's also calculate 0. Well, 0 to the 6th is 0 mod 7. So that's, there's something different about that. But any non-zero number seems to work. That is to say, at least in this example, we've computed that a to the 6th is equivalent to 1 mod 7 for any a which is not 0. That is to say, a is 1 through 6 mod 7. Well, that's a special case of Fermat's little theorem. The theorem says, and it's called little theorem sometimes, not always, but to distinguish it from Fermat's last theorem. If P is a prime and A is not equivalent to 0 mod P, then A to the P minus 1 is equivalent to 1 mod P. That is, take any non-zero number, mod P, and raise it to the P minus 1, and you always get 1 mod P. Okay, let's do a couple more examples. If P is, let's take A is equal to 2, P is equal to 5. Well, 2 to the P minus 1 is 16, which is indeed 1 mod 5. And if P is 11 and A is still 2, you get 2 to the 10th, which is 1024, which is, let's see, we're doing this mod 11. Well, 1024 is 1023 plus 1, and 1023 is divisible by 11. So again, you get 1 mod 11. Now let's do an example where you take a non-prime instead of P. Let's take 6. So let's take 2 to the 6th minus 1, which is to say 2 to the 5th, which is 32. And we're working modulo 6. This is equal to 2 modulo 6. So we didn't get 1 modulo 6. And that's okay, because 6 is not prime. The statement is that a to the p minus 1 is 1 if you start with a prime. Okay, so here's a restatement. I'm going to state it again as a theorem. So again, p is prime. And the first statement is that a to the p is equivalent to a mod p for all integers a, whether or not there's 0 mod p. So this is similar to the statement we had before, except it's a to the p instead of a to the p minus 1. And this statement is true for all a. And the second part of the statement is the one that we had before, which is a to the p minus 1 is 1 mod p. But that's only true if a is not equal to 0 mod p. So the only difference between these two statements is the first one holds also when a is equal to 0 mod p. And so let's do an example. Let's take p is equal to 5. And let's take a is equal to 2. The assertion is that 2 to the 5 is equal to 32, which is 2 mod 5. That's statement 1. 2 to the p is equivalent to 2 modulo p. And statement 2 is that 2 to the 4th is 16 is equal to 1 mod p. So both of those statements are true in this case. And on the other hand, if you take a as 5, then 5 to the 5th is 0 mod 5. But 0 is the same thing as 5 mod 5. So statement 1 is still true. 5 to the 5th is equal to 5 mod 5. That's a lot of 5s, I know. On the other hand, statement 2, 5 to the 4th, is what? 125. And that's 0 mod p, which is not 1 mod 5. So statement 2 doesn't hold for 5. And that's exactly what it says, because 5 is not equivalent to 0 mod p. So I'm just illustrating that both of them hold for a is equal to 2, but only the first one holds when a is equal to 5. Okay, so here is another result. Again, let's work mod p. And I'm going to ask a question here. When is b to the x equivalent to b to the y mod p? So you have some fixed b, and if b is 0, it's obviously true. So let's say b is not equal to 0 mod p. So b to the x is b to the y mod p for different powers x and y. And when are those equal? Well, it's kind of obvious wrong guess is to say, well, if x is equal to y, equivalent to y mod p, since we're working mod p. But that's not the way it works. And the theorem says that, in fact, b to the x is equivalent to b to the y modulo p if x is equivalent to y, but not mod p, but mod p minus 1. Okay, so that's the content of this theorem, is that in the exponent, what matters is x and y modulo p minus 1. And the way to remember this is the following key example, which is really what it comes down to. Let's take x is equal to p minus 1 and y is equal to 0. Those two numbers are equivalent, mod p minus 1. Well, b to the y is b to the 0, which is 1. So the statement says that b to the p minus 1 is equal to 1 mod p. And that's exactly Fermat's theorem. So that shows you why x and y differing by p minus 1 is what matters. And the proof of this theorem is quite straightforward. I want to know, when is b to the x equivalent to b to the y mod p? Well, I'm claiming if x is equivalent to y mod p minus 1, then it's going to work. So that says that x is equal to y plus some multiple of p minus 1, and therefore b to the x is b to the y times, y plus k times p minus 1, which is b to the y times b to the k times p minus 1. And that's b to the y times b to the p minus 1 to the k. That's the way exponents work. Okay, and now those are just integers. Let's reduce this mod p. This says that b to the x mod p is b to the y, b to the p minus 1 to the k mod p. And now the crucial point is that by Fermat, this b to the p minus 1, that is 1 mod p. So you can get rid of it. That term just goes away, and you conclude that b to the x is in fact b to the y mod p. Okay, let's give a proof of Fermat's theorem. The first thing is to prove the following lemma. We're going to work mod p, where p is prime. And we're going to take a number b, which is not 0 mod p. So it's just not divisible by p. And consider the following set. The set of integers b and 2b and 3b and so on. All the multiples of b up to p minus 1 times b. So there are p minus 1 of these integers. And let's reduce them all mod p. Okay, so now it's a bunch of integers, except you can reduce them. They're each reduced mod p. And the claim is that what you get is exactly the set of numbers 1 through p minus 1 modulo p. So these p minus 1 numbers that you started with, each one of them is equivalent to a number 1 up to p minus 1, and you're getting each of those numbers exactly once. So let's look at an example to see how this works. Let's take s is p equal to 5 and b is equal to 2. So the set is 2, 4, 8, 16, the multiples of 2. But when you reduce those mod 5, you get 2, 4, let's see, 8 becomes 3, and 16 becomes 1. And there you have it. These four numbers that I started with, when you reduce them mod p, you get exactly numbers 1, 2, 3, 4, each of them occurring exactly once. That's what the theorem, that's what the lemma says. Okay, so let's prove the lemma. So suppose a is some number which is not 0 mod p. And consider the equation b times x is equal to a mod p. I claim that has a solution. You can find an x which makes this true. And the reason is that since b is not equal to 0, b is invertible mod p. Right? And so you can multiply both sides of this equation by b inverse modulo p. And that gives you that x is equal to b inverse times a modulo p. And that's a misprint here. It's not p inverse, it's b inverse. Okay, so every a can be written as a multiple of b when you reduce things mod p. And obviously this x is not 0. So what I'm saying is that this a is b times x mod p for some for some x, and it appears on this list of multiples of b. Some multiple of b is equal to a, and so it appears on this list. And every a occurs. So, in other words, all of the non-zero a's show up on this list. That's what I needed to prove. Now here's the proof of Fermat's theorem. Suppose P is prime and A is not equal to 0 mod P. Now you do this funny thing which doesn't seem to have anything to do with it, but it does, which is you write down this product of numbers 1 through P minus 1, that is to say P minus 1 factorial, and consider it mod P. Now, by the previous lemma, you can write that list of numbers 1 through P minus 1 is 1 times A times 2 times A times 3 times A dot 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 times P minus 1 times A, because when you multiply by A, you're getting exactly the same list of numbers, just in some different order. So I'm free to write it this way. It's exactly the same product, it's just the numbers are appearing in a different order. So these two values are equal to each other. So what does that say? Well, the second term is P minus 1 factorial. You factor out that's these numbers 1, 2, 3 up to P minus 1. So you get a P minus 1 factorial, and you get an A to the P minus 1. And of course mod P. So that's the second expression, and now the first expression, of course, is just P minus 1 factorial mod P. That's this underlined thing. So I conclude that P minus 1 factorial mod P is equal to P minus 1 factorial times A to the P minus 1 mod P. Well, can I cancel the P minus 1 factorial from both sides of this? Well, I can if that number is relatively prime to P, which it is. So that's a legitimate step. And what do I conclude? I get 1 mod P is A to the P minus 1 mod P. And that is Fermat's little theorem.